Well, what we're doing here is just checking the temperature of some MOSFETs that are currently dimming about 600 watts of incandescent light bulbs, and well, this is the temperature sensor, and the normal room temperature is about 25 degrees, but I've got a lot of lights on at the moment, and it's getting quite warm in here, so even the ambient temperatures up to about 29 or 30 degrees, as you can see here. And what I'm trying to do here is use the analog to digital converter on the microprocessor, which is a small ARM chip, to check the temperature of the MOSFETs. And here we've got a little thermistor that's sitting on this heatsink. Now the heatsink's actually quite large now. It was a lot smaller, and the devices got fairly hot, but they're not running too bad. You can actually, it's running 600 watts, and you can actually touch them, so got to be careful. This is live, and if I poke around, I can take an actual reading right next to this thermistor. We're at 38 degrees, 39 degrees. I've also got these other channels also turned on, but I'm really just interested in this this channel of the dimmer. So if we're at about 38, 39, maybe 40 degrees maximum, but that is that's a little way away from the actual transistor. And of course the transistor's got a plastic case, and the actual semiconductor chip itself will be much hotter than this thermistor and anywhere around here. So what I often do to actually try and get a better idea of what the temperature in the device is you actually touch this little sensor probe onto the pin of the transistor, and you can see, got to be careful again not to short things out or touch it, but that's at 51 thereabouts. This one is again 51 degrees, so you can see, and the actual chip will still be a bit hotter than that inside the package. So you've got to be careful of the actual chip temperature, not what the temperature around here is. So it's no good turning things off if this gets too hot or above close to the transistor's critical temperatures. You have to actually allow for the fact that the heat is lower here than it is actually on the chip itself. So that's a perfectly comfortable temperature. It can go hotter than that without any real concern. I don't want that to get much above 70 degrees, maybe 80 degrees, because again inside the chip it's going to be that much hotter. I could check the actual operating temperature of these chips. It is probably well over 100 degrees, 120 degrees, but you don't really want to get anywhere near that. The other contribution to heat on this board are the resistors that measure the current, because we also have a current sense, and these things are getting quite warm. They're only 82 milliohms, but they're running up to about 60 degrees. So that's actually 61, 62, even higher, 66, and 60 there. Well, now these are 1 watt resistors, and I think that. I don't really want them to get that much hotter, so I may have to do something about that. But the processor's also got its got a temperature sensor built into it, and the processor's running. Well, it's not the processor getting hot; it's the heat from the resistors that are conducting on the circuit board that's warming up everything else on this board. The actual processor won't be generating much heat of its own accord, but that's okay. That's still quite warm, but it's well within operating parameters. Now, what I'll do is I'll just show you the lights. We've got a nice array of lights doing the testing the dimmer, but also warming the room up quite nicely. And I'll just come over to the program that's running. It's, if I can get this close, you might be able to see here the IDE for the processor is attached to the processor, and this DR here, that's the data from the A to D converter. So I'm not doing any specific computations on that. It's just a number that I'll average and use to either turn the levels down to prevent it overheating. So that's where we are at the moment, and I'll see whether I can add some more later.